Well, I can hardly believe we're in our fifth week together, looking at statistics, and data, and using data to transform practice. And this week, in our fifth week together, we're going to take our first look at multivariate models. And we'll focus on two, the ANOVA and the Kruskal-Wallis test. We'll talk about what those statistics do for us and how they help us transform practice, how they operate. So as you know, we're in the analyze stage of our Emory roadmap. We've worked on drafting our questions, designing problem statements that then guide us in how we examine the data. We've explored the data looking at central tendency, distribution, variance, relationships among variables, and creating subgroups to fine-tune our analysis further. And now that we've done that, we're moving into our analysis phase with our t-test and our Wilcoxon rank sum from previous weeks. We use those to look at relationships between two variables. And in this week, we're going to use multiple variables and see how that can add another layer to our statistical skills and our power to understand practice data. So we'll be using these tests to look at the differences between groups. So in previous examples, we compared two variables that had categories A and B, or two different means or two different medians. Now we're going to be looking at groups that have more than two in them. And the first approach we're going to use is a parametric approach. And this one assumes that the data that we're looking at are normally distributed. So we'll have identified if this is the right test by doing our exploratory analysis, looking at the means, medians, interquartile ranges, standard deviations, and our histograms. And that will help us know if this is the right test to use for our data. So our discussion today assumes that you've already done that descriptive work and you know that the data are normally distributed so that this test will fit. So the first technique is the analysis of variance, or a one-way ANOVA. You can see here that analysis of variance is just the basis of this acronym ANOVA that we'll look at. And ANOVA's purpose is to compare the means of multiple groups in one test. Instead of running 5 tests to compare 5 different groups, you're able to run one test and compare them all at the same time. And what we're going to be doing is looking at the cases of the number of clients who are discharged from hospitals by region. And we're going to use that as our test case to illustrate this statistic. So if you would take a moment, go ahead and open up your data set that you saved from week 3, or week 4 rather, where you created the regions, and also week 3 that includes the numeric states in it. So bring into SPSS your most recent data set so that we can benefit from all of that work that you've done on those variables. So let's go ahead and run some descriptives here on this, this variable for the number of readmissions. So go to Analyze, Descriptive Statistics, and Descriptives. And let's select our heart failure readmission number from our variables. We'll pop it into the variables window, and then you can look at the options, and it will give you choices about which descriptive statistics to use. So let's suppose for a moment we don't know how this variable is distributed, whether it's normally distributed or skewed. So we're going to pick the mean, and as well as the standard deviation, which would be appropriate if it's normally distributed. And we're going to have the range, minimum, and maximums as well that will help give us a better understanding of how this variable is distributed. So let's run that analysis and see what we get. So for the heart failure readmission numbers, we have 2,800 observations. Range has a total range of 868, the minimum of 11, maximum of 879, mean of 90.7, and standard deviation of 82. So if we look at that, we see that there's quite a large range from 11 to 879. And that might be because these data are normally distributed, or it might not. We can't fully tell from this descriptive analysis. So what I suggest that we do, so here we have the descriptive output, and you can see that on the heart failure readmission numbers, we have these trailing decimal places for the minimum, maximum, mean, standard deviation. And since we're looking at absolute whole numbers of readmissions, one way to simplify our output is actually by going back to our data view. So we can go back to the data view and select our variables. And we've been looking at heart failure readmissions. Can select that variable. And you can see here that there are 2 decimal places, but we don't, sorry, that one's the excess, rather. We don't want to change decimals there. We're looking at the total number of readmissions. So let's continue to scan up and select that one. So here we have heart failure discharge numbers. So that should be a whole number. We don't need any decimal places in there. So we can click on the decimals, the drop-down menu, and remove them. That will simplify our output. And we also have the heart failure readmission number here, so we can eliminate those decimals as well. Now when we go back and run our descriptives, without those decimals, it'll be a lot easier to read and interpret. So let's do that. If we go to Analyze, Descriptive Statistics, and Explore, I'm going to pull the pneumonia readmission numbers, and let's stratify it by the regions that we've created in our previous week, the regions from Health and Human Services. So we'll add the regions. Now on the statistics that we want, we're looking for the descriptives, so that's correct. The plots, we probably would like to have the histogram as an easy to interpret, to look at if there's differences by region, and we'll say take the default in the options. Don't need to change anything on the defaults. And in the display, we'll take both statistics and plots. We'll say, all right, let's see what that looks like. So here you start with a summary table of the region and how many observations there are in that region. So you can see there are very few in Alaska, Hawaii, only 9, and 603 in the southeast. So quite a range in terms of the number of observations that the summary statistic for each region is based on. Now, before we look at the detailed descriptives here, let's scroll down and look at our histograms. They're an easy place for us to start understanding differences in region. So if we look at the bottom, we have the total number of pneumonia readmissions by facility and how often that number of readmissions occurs. So you can see most of the data are clustered here on the left-hand side of the diagram with a right-handed tail. So these data are right skewed. That's New England. Let's scroll down and see if that pattern holds true in all of the regions. You can see here there's quite a bit of difference in the western region. We do have some heavy clustering on the left-hand side of the graph, but there isn't a clear drop-off with a clear right tail as we had in the other in the New England region. And the same here in the Southwest. There's a heavy clustering on the left of the diagram, a little bit of spiking, but there isn't the same clear pattern that we saw in New England. The Pacific Northwest, again, doesn't match the pattern of New England, and Alaska and Hawaii's pattern is quite different. So you can see, looking at the histograms, we have differences in the distribution of this variable. If you want to go back and quantify and put numbers around the pictures that you're seeing, you can go into the detailed descriptives that are output here. So on number of pneumonia readmissions in New England, the mean number of readmissions per facility is 73. the median is 59. So you can see the median is lower than the mean, and that pattern of the data being clustered on the left-hand side of the diagram held true in the histogram. So you can then, after you look at those measures of central tendency, you can look at the spread of the data, looking here at the interquartile range of 59 and the standard deviation of 54. So then you could go region by region and make comparisons looking at these numbers. Now, with 11 regions and all of these measures of central tendency and variance, that would become quite cumbersome. So the good news is we have a statistical tool to simplify that analysis for us, so we don't have to go through point by point. So let's look at the ANOVA as one statistical tool and see if that tool would help us understand differences by region. So again, the purpose of the ANOVA is to compare multiple group means in one test, which is exactly what we want to do. Like every test, it has assumptions, and for ANOVA it assumes that the groups are independent of each other and randomly selected, that the outcome measure is occurring on an interval to ratio scale, and the variance between the groups is equal. So when we look at the spread, how much spread there is around the measure of central tendency, we're looking for standard deviations that are very similar or interquartile ranges that are very similar. And also that the data themselves are normally distributed. So we saw looking at New England that the data actually are not normally distributed. They have a heavy clustering on the left with a tail to the right, so they're right skewed. Now, the ANOVA is relatively tolerant to violations of normal distribution that are fairly small. But in this course, we're going to always practice looking at the assumptions and picking the test that is most appropriate, where the assumptions do hold true for our data. So we can see here that the variance between the groups and the size of the groups need to be approximately equal for each region for ANOVA to be a valid test. And we saw that the variance and the sample sizes in each region are not equivalent or similar. So looking at the outcome measure of interval and ratio, we know that the outcome of the number of readmissions is an interval measurement, and the assumptions that the groups are random and independent, we can't fully verify because we don't know all of the backstory of which facilities are included and not. And I'll say for the purposes of ANOVA, oftentimes practically this assumption is not always fully met. We don't always have full independence of groups or complete random assignment. And in that case, again, the non-parametric test is going to be our most conservative and best test to use. But I'm going to demonstrate for you how to run the ANOVA using these data. So even though we know that ANOVA might not be the best test for comparing regions, I'm going to use this as a way to demonstrate how to run ANOVA. So you see the mechanics, even though I'm not advising that you actually use ANOVA in your analysis. I want to demonstrate the process. So if you go to Analyze, Compare Means, we're going to do in one-way ANOVA here. We're looking at the number of heart failure discharges by region. You can go through and look at the contrasts. You don't need to change anything in that menu. You don't need to modify the post hoc menu. You can add some descriptive statistics here in your output, and we'll say, okay, show us what that does. When we run the analysis, we see that each region is displayed here on the left, and the means are displayed in this column. You can visually see that there's quite a variation in mean. We have 205 here, 493, 535. So that variation in the mean, as well as the difference in the n, or the size, the number of facilities sampled, should tell us that ANOVA is not the best test. But let's come back in our next session and interpret it. So have a great week on ANOVA and Kruskal-Wallis, and we'll interpret in our next time together.